Okay, I just wanted to give a quick summary of the homogeneous differential equation solution before we look at the non-homogeneous. We'll see if my voice lasts that long. So we're solving ay double prime plus by prime plus cy equals 0. If we have b squared minus 4ac is greater than 0, as we solve the characteristic equation, right? Then we have two real distinct solutions to the characteristic equation, R1 and R2. And then we have the solution to the differential equation is a linear combination of C1, well, e to the R1t and e to the R2t. Those are our two solutions. Good. And if we have a complex roots to the characteristic equation, we'll just say that R is alpha plus beta I. Notice that you don't need both of these. Then our solution can be written as C1 times the real part of e to the RT plus C2 times the imaginary part of e to the RT. If you don't like this notation will be handy later on. But for right now, it's okay if you want to just remember it as C1 times e to the alpha t cosine beta t plus C2 times e to the alpha t sine beta t. And the important thing here is that there is no I here, right? There is no I here. This is a real solution. Good. Finally, if b squared minus 4ac equals 0, that was our last case, then we have one single real solution to our characteristic equation. And so in order to get y1 and y2 that form a fundamental set of solutions, we're going to take e to the rt and multiply it by t. And so e to the rt is one solution, and te to the rt we showed is the second solution. Good. Okay, that is how you solve ay double prime plus by prime plus cy equals 0. Now, we want to extend that a little bit. We want to solve the non-homogeneous differential equation now. All right. And so I just wanted to introduce a little bit of notation first. If we're looking at ay double prime plus by prime plus cy equals 0, boy, I can say that real fast. Or the linear operator equal to 0. The solution to that is going to be called the homogeneous part of the solution, or y sub h. So this is y sub h, where h stands for the homogeneous part of the solution. Similarly, if I have the non-homogeneous differential equation equal to g of t, or if I just have the linear operator equal to g of t, right, then the solution to this equation, either of these equations, is going to be called the particular part of the solution, or y sub p of t. Okay, good. So how to solve L of y equals g of t in general? The full general solution is y sub h of t plus y sub p of t. You take the homogeneous solution and you add it to the particular solution. Now this might be kind of odd, right? Because if you've got a solution to the differential equation equal to g of t, what is this doing here? Why do we need this? Well, the answer is, and we're going to just show it in a minute, but the answer is that y sub p of t will have no general constants, arbitrary constants in it. Everything in y sub p of t is going to be defined by g of t. And so therefore, if you were to ignore y sub h of t, you would have no constants to solve for the initial value problem. Okay, so the constants for the initial value problem are all going to be contained in here, the y sub h. And now I've probably given it away. Let's prove that this is true. So if I plug y sub h plus y sub p into my linear operator, of course, because it's a linear operator, I can pull it apart and I get g of t. Good. All right. And so just again, just to emphasize, all the constants to solve for the initial value problem are going to be contained in y sub h, right? Because you can multiply y sub h by c and still get 0, but if you multiply c times y sub p, do you get another solution? No, you don't. You don't get a solution. So the arbitrary constants then for the initial value problem are going to be all contained in the y sub h, in the homogeneous part. Okay, we'll see that in just a bit. Okay, a bit more theory. Suppose I've got my linear operator equal to a big sum of different functions, g1 through gn. The beautiful thing about a linear operator is that you can break it apart into n different and smaller problems, right? So we'll look for the homogeneous equation, then we'll look for where L of y is equal to just the first function, g1 of t. Then we'll solve for where L of y is equal to just g2 of t. Then we'll solve for just where L of y is just equal to g3 of t, and so on until we finish, okay? What do you do with all these solutions? We're going to have y sub h, y sub p sub 1, y sub p sub 2, y sub p sub 3, all the way up to y sub p sub n. N plus 1 different solutions to our differential equation. What's the general solution? It'll be the sum. That's what linearity gives you, right? This is really at the heart of linearity, is that if you can solve these complicated differential equations by breaking them apart and then adding the solutions together. So that's why they're such an important class of differential equation. All right, let's see if we can do an example. Y double prime minus y equals t. Okay, so the first thing we need to do is find the homogeneous part of the solution. So if we do that, we get our characteristic equation, r squared minus 1 equals 0. So therefore, r is equal to plus or minus 1, and so there's our homogeneous. Now to solve for the particular part of the solution, I'm noticing here that I have a polynomial of degree 1. And so I'm just making that observation that if I differentiate a polynomial of degree 1, I get another polynomial, right? And so I think I can guess what the solution is going to be for this differential equation because of that fact. And so because the derivative of a polynomial is a polynomial, and I want a polynomial of degree 1 out, then I'm going to guess that the solution is a polynomial of degree 1. Okay, by guessing that, I have two arbitrary coefficients, and I have to figure out what those undetermined coefficients are. So in order to do that, I plug this guess back into the differential equation, and I solve for a and b. So in doing that, I need the derivatives. I made this an easy guess so that the second derivative is just 0. First derivative is just a, and so we just end up with a really simple equation. But you can see here, right, that b is going to have to be equal to 0, and a is going to have to be negative 1 for this to work. And so therefore, we have our solution. Our full solution now is c1 e to the minus t plus c2 e to the t minus t. And of course, you're seeing here, right, that this is y sub h. Y sub h has the arbitrary coefficients. Y sub p has a specific polynomial. Very good. So this is what we're going to be doing in the method. This is section 3.5. The method of undetermined coefficients is a method of guessing what the solution is based on the right-hand side. And so some classes of the forcing function f of t are particularly nice, because what happens when you take the derivative of a polynomial? You get another polynomial. It's a degree 1 less, but that's okay. What happens if you take a polynomial times the exponential function and you differentiate? Well, you have to use the product rule, right? And in fact, what ends up happening is you get another polynomial of degree n times the exponential function. So in fact, in this case, you do get another polynomial of the same degree that you started with. Okay. Similarly for sine, if you differentiate this, you would have polynomial and a cosine, and this one would give you a polynomial and a sine. And so when you're dealing with sines and cosines, you have to be sure that you're going to include both the sine and the cosine when you're going to give a guess. So we're going to have a polynomial of degree n times the sine and a polynomial of degree n times the cosine. Okay? Well, we'll see how this works in just a second. I'm just giving you some intuition about why it works. Okay, finally, if you have a polynomial of degree n times the exponential function times the sine, this is as complicated as it's going to get. Polynomial times exponential times cosine, the same thing happens, right? The exponential function just kind of comes along for the ride, and you're going to get something very similar. Good. All right, so let's see how this is going to work. Let's just look at some specific examples for our right-hand side. Suppose I've got t squared plus t. What would I guess for my y sub p? Well, because this is a polynomial of degree 2, I would guess a degree 2 polynomial. Good. And then of course I would have to plug this into my differential equation and solve for a, b, and c. Okay, next, e to the 3t. What would I guess is the solution what would I guess the form is for y sub p of d? A constant times the exponential. Very good. Next one, sine of 3t. What would I guess for my particular part of the solution? Now this one's a little bit tricky, I should say, because it's not just sine, but you also have to put in a cosine. Because remember, derivative of sine is cosine, so you have to keep them both. So in fact, the solution, or the guess, will have to be a cosine 3t plus b sine 3t. Okay, so this is my full y sub p now. And I would have to put this into the differential equation and solve for a and b. Good. How about t e to the 2t? What would you guess? Well, the way to think about this is a polynomial of degree 1 times the exponential function. So I'm going to guess a polynomial of degree 1, a full polynomial of degree 1, times the exponential function. Good. Similarly, this is a polynomial of degree 1 times the sine. So I need to guess a full polynomial of degree 1 for the sine and a full polynomial of degree 1 for the cosine. Oh, usually I put cosine first. Oh well, it doesn't matter. Okay, how about this one? T e to the minus t sine of t plus e to the minus t cosine of t. You'll notice that here we have a polynomial of degree 1, and here we just have a constant. Now you could break this up, but actually there's overlap between these two functions as a pair, right? And so you don't have to break these up. In fact, I would say don't break these up. Make it one guess. And so we're going to guess the polynomial of degree 1 times the sine function plus the polynomial of degree 1, a different polynomial of degree 1, times the cosine. And then just keep in the exponential function. Did you get that one? That was probably the hardest one. Okay, there's one more thing to keep in mind, but we'll wait on that. All right, whoops. Did you see that? I'm going to pause here for a minute, and I'm going to have to break up the slides or the talk into a couple different pieces. So we'll pause here. This is the method of undetermined coefficients, where we guess the form of the solution based on the form of our forcing function, right-hand side.